I'm going to just redraw this quickly. So when you consider this point and that point, then goes up there, then the way we look at is that portion of the wave is all coming down. This is all compressing the water. Then after it reflect, and this is image charge. That's what I said, easiest way to explain the rarefaction wave. Fluid, this is whole infinite number of fluid particles are here. So it's a collection of infinite number of water particles. The water particle is attracted by image source, so it's gonna be kicking in that direction. As water particle is moving toward the image charge, the wave front is moving toward the target. So water particle is moving in that direction, but the shock wave front is moving toward the target. In other words, the direction of the motion of water particle is opposite to the direction of the motion of the shock wave. So that's the situation. It has to, the particle has to kick out. Otherwise, if whole water is so tightly held together, if the particle is holding all together, doesn't separate, then rarefaction wave doesn't occur. Okay, that's the situation. So so this is one good example. Another example I did yesterday was, what about the sea bottom? So of course the impedance, I haven't talked to you about the impedance. Impedance is really defines the acoustic property of the media. So the water could have a rho C, and this sea bottom here depend on the soil property. It could have a different the value of the rho C. As you will see in chapter 3, this will act like a damper. You know, damper, that's what the shock absorber is, damper. Water is like acting as a damper, or like a spring. That's what the rho C is here. So here, anyway, so for this, to get the reflection kind of the diagram I mentioned to you, it could hit the target, but this is a compressive wave, this is compressive wave, this is compressive wave, that portion is a tension wave, okay? So that's the reason near the free surface, plumes, white plumes, you see that. So sometime this week or early next week, I'm going to show you the movie clip. But in addition, this is one media to the other media. This is one media. This is like air. This is one media. This is another media. This is like a solid. And it can propagate. The wave can propagate, go into, transmit into the ground, the sea bottom, then could come out that way, whatever. Okay, this is called, this kind of the wave is called refraction wave. or transmitted wave. There is another kind of a wave. Surface wave belong to this class of the wave because surface wave is going through the surface. There are not many different waves. It has just a few types of the wave you're gonna deal with as a shock wave. Okay, it's not that bad at all. And I mentioned to you about the about these two equations, this T and R. This T, what is the T? I'm always checking. What is the T? Okay, when you deal with the T and R, that ties with what? What's the T here? When you hear about the T and R here for this equation, this has a connection to the gas bubble motion, right? You got the gas bubble. So explosion, underwater explosion really means explosion in the water, right? So at the time of explosion, detonation wave develop and propagate in radial direction with the speed, detonation speed of about what? You decided not to talk. About what? Chorong, what? What speed? At the beginning. If you don't know this, you can't understand, you can't tell what happened at the time of detonation. What speed release? About 8,000 meters per second. That's a detonation speed. To really study what happened right in the vicinity of the charge at the time of explosion, or what happened inside the explosive where at the time of detonation, you have to study detonation physics. This course is Naval Ship Shock Analysis and Design courses. Anyway, then the detonation speed converges down to what speed? Acoustic speed, which is about 1,500 meters per second. Then it propagates. The kind of the work is what happened to ship when shock wave propagate in the acoustic speed range. Why? If explosion occurs very next to the surface ship or submarine, what do you have to do? You know, I told you, right? I told you. You have to pray hard. Why? It will puncture the hole anyway. You can't stop when explosion occurs very next to the target. It will blow. You can't stop that. So we study what happened. When the explosion occurs in the range of about 10 to 100 the radii or radius of the charge. That's really estimate, you know. It's not, it's like a rule of thumb you call. So when explosion occurs right there, you have nothing to solve for problem. But when you have, when explosion occurs about here, whose distance is, of course, whose distance, this is like a charge, this is charge, okay? Radius is, let's call R. If this distance is about 10 to 100 radii of explosive charge, radius of solid explosive depend on the size of the charge. So if this distance is about 10 to 100 times the radius of explosive charge, in that range, then you can do a lot of things. All the empirical equation is kind of a valid. So in this range, all the empirical equations shown in chapter 3 are all valid. Then if you say what happened after 100 radii, maybe 1,000 radii, what happened? That's okay, I will say. Okay, you have no other the empirical relation to explain, it's all valid. Of course, it's all valid. It's an acoustic range. Shock wave is so small. So this is a unit-dependent equation. And this is the second. W is in pound force, right? So 1 kilogram is about 2.2 the pound force, okay? You can use, I demand you use both the unit, not just the matrix unit. So pound force, sometimes using like this, some people just use this, okay? And don't use pound mass here. It's confusing. So I don't use this. For the US gravitational unit, I'm using this, and of course, so this is mass, the weight, and this is time. Another one is what? Use feet or inches, which is length. And for the matrix, what do you use? You use a kilogram. You use a mass. And you have the length is a meter, and time is the same. You use a second. Then equivalence, you take a look at conversion table. In the internet, you can use all of that. And R, very important parameter, which is what? Louder. Radius of gas bubble, which is maximum radius of gas bubble. Okay. Maximum radius of, this is unit dependent. The feet, pound, this is a pound, D is feet, which is a charge depth of the charge from the free surface, okay? So, and these two quantity is kind of important in a sense that W is a TNT equivalent charge weight. So there are, as we did in pure explosive and high explosive area, we look at the pure explosive, or sometimes called the primary explosive. Another one is called high explosive, or the mixed explosive mixture, or slightly different name, who cares, right? So there is HVX1, there is a TNT, there is RDX, there is C4, all different kind. And Korea, they're using also different kind of explosive. So here, TNT and HVX1, there is RDX type, there is the other type, C4. But most typical standard is TNT. Everything is referenced to TNT. Okay, so this is all the type of high explosive. HVX1, this is U.S. Navy is using HVX1 for like a ship shock tryer, very popular explosive. And but this is about 1.5 times stronger than TNT. So when you compute the charge weight over here, if you use HVX1, let's say you use HVX1 100 pound, okay? Then you have to multiply the factor to convert into the equivalent TNT weight. So factor is roughly 1.5. So you have to multiply 1.5. What that means is 100 pound HBX1 has, to get the same strength if you use TNT, you have to use how many pound? 150 pound. Okay. So that's what, some others, the strength's about the same, then you don't have to worry about it. So now to how to get the 33 feet is 14.7 psi. What's the 14.7? That's the atmospheric pressure in pound per square inch, right? That's a psi, but in bar. So when you convert into, I prefer you use this in US gravitational unit, then convert. First convert, if you have a metric unit, into US gravitational, then you get the T. Or you get the feet, then you convert into metric unit. So either way, that's up to you, okay? This R and T, and that's the way you can get the 14.7. What's the 144? If I keep talking with the PowerPoint, I have to be very careful, because you just watch, then it just goes away, coming in from one ear, goes out to the other ear, so then get lost. That I have to really prevent. So 144, Charong, where that 144 came from? Right. So 14.7, you have to convert 14.7. This is really pound per inch cube. So I want to convert this guy to pound per feet square, because later 62.4, that's 62.4 is pound per feet cube. That's the water weight. But you can use water weight in metric unit. All my notes in pound feet or inch and second. That's the reason I want to convert this guy. Inch is, I want to convert this guy as a pound feet square, right? So what shall I do? Convert inch to feet. You have to multiply. 12 inches, 1 foot, right? And square, 12 square. Then that's 144. That's what this 144 comes. So when you do that, that's inch square. So, 12 square. So it's 1 over 12 square. Inch square is 1 over 12 square. So that's what the 144 comes in. So 144. So this is atmospheric pressure in pound feet square, right? Conversion. Then I want to change, then get the hydrostatic head. This is feet, multiply D. D is in feet, right? So then you can compute the equivalent hydrostatic head. Simple. So it's a 33. What that means is we are under atmospheric pressure. We don't feel it. But when astronaut was out in the space for a month or 6 months, when they come back to the Earth, they are under the gravity, right? Under the gravity. So they can't even stand because they feel the pressure. So much pressure, but we don't feel pressure because we always sustain that gravity force. But astronauts, they were under no pressure. When they come back, heavy pressure. So here, this is equivalent the atmospheric pressure. That's what to convert into that. So that's a 33 feet. So we are under pressure of 33 feet, which is you divide by about 3, about 10 meter, 11 meter, 10 meter of the hydrostatic pressure. Always. So pretty heavy, isn't it? So that's what that 33 comes up. And R and T. Then you can compute the T. 1 over T, what do you call that? 1 over T, frequency, right? So you can compute, now you can compute the oscillation period or oscillation frequency of gas bubble wherever explosion occurs in the water. Then also you can compute the maximum gas bubble. So maximum gas bubble, why do we have to study that? Why we need that? For example, why we need that? Ship is a neutral buoyancy. This is very long, like a destroyer class ship, 세종대왕 ham, the Korean DDG class ship. Length is roughly about 450 feet. So you divide it by about 3, so about 150 meters, 100, maybe 60 meters. Pretty long. 150 meters long. It's like a beam-like structure. Submarine, same beam-like structure. What's the usually when the vibration occurs, what's the usual, the mode of vibration? Fundamental mode of vibration, bending mode. It's just this is the first mode. Flop that way, flop that way. With very low natural frequency. Okay? Let's say 1 hertz. Okay? This gas bubble oscillates very low frequency. Could it be 1 second? Less than 1 second. Let's say 1 second. Then what's the frequency, gas bubble frequency? 1 hertz. 1 over T. So excitation frequency is 1 hertz. And the ship natural bending mode frequency is 1 hertz. Then what happened? Then they love each other. Then when they love each other, what happened? They embrace each other. Then what happened? Then they could marry. Then things blow up. In other words, resonance situation occurs, right? Resonance situation. With the small input energy, you just input small, but resonance occurs. But deformation response is huge. Okay? That's what happened. That's what we have to worry about it when you design and perform the analysis for ship shock problem. And R, well, you have to compute R for one example. For Cheonan naval ship shock situations here, explosion occurs right there, not far, maybe about 6 meters, roughly, from the free surface. About 300 kilogram explosive. You can compute the R, the radius of the charge, radius of gas bubble. Shock wave hit and gone. Then this could lift up. This could lift up. Gas bubble radius is something like 18 meters. We compute it. 18 meters. 18 meters, this gas bubble lift this whole ship up, move up. Then very heavy weights here and here. Propulsor could be not exactly here, propulsor roughly here, and sonar system, everything's all there. It lifted up this ship like shape goes like this. Then gas bubble doesn't stay to max. It's down to min, right? Then collapses, down to min, then it collapses, its gas bubble goes down like this. Then this guy bend into opposite direction. At the beginning goes like that, and after that goes up or down. It's called the whipping. Whipping. So that's why we need to compute T and R. Very important. So to really check it out whether it's going to happen resonance or not, easily or not. And the motion goes like this for the gas bubble. This is a time, this is gas bubble radius, I call the gas globe. It's the radius of the gas bubble. As time at the beginning, it's really small. It's simply the powder. then at the time of explosion it grows, gas bubble grows. Gas bubble grows as time goes by. Then to the maximum here, gas bubble radius become maximum here, then get down to the minimum here. And the gas bubble goes big, and it's gonna go big. How far? We talked about that before. It grows to the limit. What's the why it stops? Because hydrostatic pressure plus atmospheric pressure could be about the same as the gas kind of the pressure in the gas in the bubble. Then stops, but it will go a little bit more because of the inertia effect. Then go down to the min, right? Go down to the minimum. Gas product is all still in there. As it gets down to the minimum, it loses balance because of the pressure differences at top and bottom. Then it collapses. But still a gaseous product with energy, still confined in the water, someplace in the water, but it will keep migrate due to the buoyancy effect. It will keep migrate toward the free surface. So bang here, then it will go back. But now size of the gas bubble is smaller. Why? It loses energy into the water as it works in the water. Then second bubble and things like that. Then eventually as the bubble get to the free surface, then it will vent out. Our lab, all students really exercise through or research through all the gas bubble motion until it vent out in the air. And the venting out process is very important for like high-speed craft and a lot of different the vessel for the stability situations. Okay. Then here, as you look at the path of the gas bubble center, this is the gas bubble's center, path of the gas bubble path. It rises slowly. When gas is really small, then it really moves fast. Then after it starts, as the bubble really grows, then it moves very slow. The migration means it's really the motion of rising motion of the gas bubble. At the beginning slow, bang, then it suddenly moves fast, then slow, then fast. When I give a lecture in electric boat in Groton, one engineer raised the question, why when gas bubble is really small, then its speed is suddenly getting higher. It just goes up quickly, then it gets down to slow. Then, at the beginning, right here, slow. Slowly goes up. Then, when gas bubble is really small, goes up faster. Then slow, faster. Why does it do that? When gas bubble is very slow, he said, I expect gas bubble, when the gas bubble is large, buoyancy force is large, then it should move fast. And when gas bubble is slow, buoyancy force is small. Then it should move much slower. Then why it happened? Do you have any idea? Why it could happen? energy release. What happened to Hassan and Lee? They thought maybe we don't have a class today. I clearly said we have a class today, right? So what happened is when a gas bubble is large, then there's a large drag force. Drag force on the surface of the gas bubble. So the bubble tried to rise it, but a lot of resistance through the drag forces for the surface of the gas bubble. So it doesn't rise. But when gas is small, drag force is much, much smaller. So in other words, the effect is a lot higher for the drag type of the forces. And as a gas bubble is large, you can say the added mass, the effect is really heavy. So it's resisting the migration of gas bubble. So that's the reason. But that's really easy to talk like that. How we're going to explain using some simple math. And here is what happened at the beginning. Explosion occurs. You have a heavy, very high shock wave pressure. Then get down to the min. It goes below zero. Goes a little bit below zero. Because water cannot sustain the tension, I said. In any computation, you can set to 0. But water can sustain 3 or 4 psi, pound per inch square. So you can goes slightly below 0. Then bang, it's a secondary pulse due to the bubble collapse. Whenever something collapses in the water, then there is a shock, which is not as big as the incident shock wave, small. Then again, the bubble comes up, then down, then bang. This could be from the bottom reflection wave, shock wave, or things like that. Another gas bubble collapse, things like that. So I draw this. This has been used by many other authors in their paper. I just draw this by Apple computer some years ago. Charge size, maximum gas bubble. Right here, gas bubble shape changes, and hydrodynamic forces is a jet flow comes right under here, then shooting up, then it keep oscillating. All my lab students did a simulation. Sometimes I'll show you after we put all that. Okay. Then, why the gas bubble rises much faster when the bubble is really small? This is the simple kind of the theory. For gas bubble, assume a sphere. Very reasonable assumption. The buoyancy force on gas sphere F is md, is displaced mass. What does it mean, displaced mass? What does it mean, displaced mass? It's the 3 over 3 pi rho. A is radius of gas bubble. Q times g, the gravitational acceleration. So this is without the rho, that's the volume of the sphere, right? Then you multiply the water mass density, then this is kind of a displaced mass, right? This is a buoyancy force, right? And times G. So this is buoyancy force, like this, right? Then a vertical momentum of gas sphere acquired by the water at that time is MAU. This is a vertical momentum of the gas sphere with the particular, the rising velocity U, whatever the U is vertical, the bubble velocity. And this MT is a vertical momentum of a gas sphere, and A here, MA, is added mass of water, which is really, some people call hydrodynamic mass, due to the drag forces or viscosity of the water, and which is kind of the pulling effect of the gas sphere. So if you convert into the added mass, the gas sphere, when it rises, it carries some layers of water in the vicinity of the gas sphere surface. Okay, it's called added mass. It's shape dependent. Anybody has a strong interest? I have a really very thin report written by Caltech, a professor some years ago. It's a shape dependent. So for the sphere, this is a 2/3 pi rho AQ. Okay, so you may take a look at. It's called the added mass. If added mass for sphere situations, and times U. Then impulse, linear impulse, is a change in momentum. You know that in dynamics class. What is the impulse? Impulse is area under the force, right? So impulse, this is a force, this is a time. Whatever here, impulse is area under. What would be the unit? Unit is a force times multiplied by the time. That's impulse. Impulse is very important quantity, which is like proportional to the damage of the system. Damage. You are dealing with impulse. Okay. So here, so linear impulse is the change in momentum. So this is impulse. The force is buoyancy force. So summing up 0 to time t, force dt. Okay. And initial momentum is, of course, 0. Initially, no gas bubble. Then start from 0 to time t. mt we computed. So if you you end up having this relation. Then you plug in what you have done. Then u is gas bubble, the vertical velocity of the gas bubble. We set the z positive as upward direction. I'm sorry, z is positive, is going that direction, is plus g. U is gas bubble motion as it going up, which is dg over dt. Okay, so u is going to be negative. We set the vertical downward as a positive. You can set this as a positive, then you have to set the positive z direction as upward. So if you put it together, u is proportional to, inversely proportional to a cube. A is radius of gas bubble. So as gas bubble is smaller, then it's inversely proportional, so it's getting much smaller. Okay? So that's the reason. That's the reason the bubble rises much faster when the gas bubble is small. In this region is small, and it rises faster. Then slow down, then fast, goes up. Okay? And this is about all. Plus means what? Compressive wave, right? Negative tension wave. This incident shock wave is a tension wave. Compression, 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 compression. Everything else is compression except the tension wave right there. Okay, so if you look at here, which the pressure wave will come first. This wave will come hit the first. Then right after, this rarefaction wave will hit, which is negative pressure. This is a positive pressure. Then as this wave hit the target, then it cuts off the pressure. So it generates so-called surface cutoff. So that's what happens. And the plumes, in terms of the plume, so right here, you will see that in the movie clip. And this is caused by the shock wave. It has, we call the spray dome. You saw it in another movie you saw. And now, first plume, this is really all white. And all white, when the bubble vent out into the air, then it's all black, which is really the powder. Explosive gas powder becomes black. And then the whole explosion process stops right there. Okay? I spent quite a bit for the 2.1 because this is the best place to explain the index phenomena. If you understood, I am pretty sure well, then rest is much easier. And 2.2, I'm going to show you the hydrodynamic relations and to get down to the shock wave. Okay.